Exploration for inviting me to give this talk, and thanking Daniel Sheehan and Dominic for the invitation and the courtesy and the comfort of the nice hotel. Basically, I'm here to talk on behalf of my colleague Marc Millis. He and I are the co-editors of the book that was published last February of 2009, the AIAA Press's book, Frontiers of Propulsion Science. And there's the book cover. And the book was designed to be an academic monograph for the purpose of reaching advanced undergraduate students, graduate students, faculty, aerospace and physics professors who are interested in exploring propulsion physics, as well as industry scientists. We start with our inspirations. The inspirations are always provided by the wonderful science fiction that we have in world literature that have inspired many of my mentors who are now long deceased and who have inspired my generation and the younger generations to come. And basically, before 1994, warp drive was only science fiction, but since that time, with the advent of Alcubierre's warp drive metric theory that was published in Classical and Quantum Gravity, the principles have now been postulated. Here, the march of scientific progress is observed, and we start with Einstein's general theory of relativity and the evolution of quantum mechanics, electrodynamics, Bondi's negative mass propulsion, Bob Forward's guidelines to anti-gravity, which appeared in the Phys Rev and American Journal of Physics. Morris and Thorne, that's Kip Thorne and his grad students, derived the first solution for traversable wormholes. And then Podkletnov came along with his claim of a gravity shield, followed by Alcubierre's publication in the Journal of Classical and Quantum Gravity of warp drive. Then we have Bernie Heisch and co-authors Hal Puthoff and so forth, Inertia as a quantum drag effect, quantum vacuum drag, and Jim Woodward's first patent on his transient Mach and inertial thruster, and Matt Visor's publication of his Lorentzian Wormholes book, which was a compendium of everything published from 1988 to 1995 on traversable wormholes, everything you wanted to know about them, including time machines, and that was published by the American Institute of Physics Press. And then Marc Millis, at the beginning of the Breakthrough Propulsion Physics program that he was the manager for at NASA Glenn, he has the space drive concepts and issues, and Hal Puthoff, my boss, has developed the polarizable vacuum and propulsion. George Hathaway was looking at null test of the Podkletnov gravity shield, and Jordan McClay and Bob Forward were looking at quantum vacuum energy propulsion. So you have that progress, and that's not everything. That's not an all-inclusive list. There were many other fields and many other topics in physics that were being evaluated. The book's purpose was to look at comparing all the possibilities of the different types of breakthrough propulsion physics that were being proposed by various investigators around the world, not just the hot topics. We were interested in explaining the physics to aerospace engineers and managers without any hype or disdain, because this is the group of people that work with the policymakers in government. They get the funding, they start the programs, and they execute them. And unfortunately, aerospace engineers aren't at the cutting edge of physics. Physicists are. So the idea is to bring the cutting edge of physics, the frontiering and breakthrough, the out-of-the-box ideas to the people in aerospace engineering who can hopefully develop programs based on these ideas. We wanted to show what can be done, that could be done next in the way of, here's what we know now, here's what's unresolved, and so there's unfinished business for students and pioneers to wrap up, to work on, to solve problems on. The guidance to distinguish fringe from frontier work, that was very important because this subject has gotten a great deal, initially at the very beginning, and it still does to a much smaller degree, a lot of derision from the mainstream academic community because they know the physics. They sit there and they look at the numbers, they look at the equations, and they say to themselves, well, breakthrough propulsion physics, there's no such thing, no warp drive, no wormholes. These things are impossible to obtain. So they think that kind of stuff is too science fiction for them to dive into. But Alcubierre's paper, Morris and Thorne's book, paper, Matt Visor's book, and so forth have all brought that into mainstream physics. This is the first rigorous book that covers the concept of gravity control propulsion, faster than light travel, related energy conversion, and managing such research. We had 18 lead authors, 27 total authors, 22 chapters, almost 800 pages. Took us almost 3 years to put the book together, and as of now, I was informed that that number is incorrect. We're approaching 2,000 copies sold, and it's actually a bestseller for the AIAA press in that series. Normally, these series in progress of astronautics and aeronautics are usually jet engine development, rocket fuels, rocket engine aerodynamics, astrodynamics, and things like that. So this was a smash hit for these guys. Marc and I were the editors. Of the lead author affiliations, 40% of them were NASA, 13% were other U.S. government labs, and 30% were private industry consultants, with 10% university and 7% foreign. And here's the list of authors. Some of whom, well, maybe one or two of whom you know. One of them is going to be a guest speaker later, Jim Woodward, and one of them is my boss, Hal Pitoff. And some of these names you may not recognize, but you may recognize Bob Forward. We have this panel of peer reviewers, which were pulled from the AIAA's Nuclear and Future Flight Technical Committee. The AIAA stands for the American Institute of Aeronautics and Astronautics, and it's a worldwide aerospace professional society. It's been around since the beginning of the 60s, and it was a merger of the American Rocket Society with the American Astronautical Society. So anyway, these were our peer reviewers. The organization of the book started this way, beginning understanding the problem, which was looking at the history of breakthrough propulsion physics, and as it was done by organizations like my institute, Project Green Glow, the NASA program, and so forth, and putting all those into context. And then evaluating the limits of interstellar technology based on the advanced physics that we know, like solar sails, beam power propulsion, antimatter rockets, nuclear propulsion, and so forth. Propulsion without rockets, that was looking at a new genre of reactionless space drives without violating momentum conservation that would cover space drive, physics primers, gravity control, non-viable approaches, and other approaches. Then the faster than light travel would be based on faster than light concepts in general relativity, such as traversable wormholes and warp drives, and then faster than light communications in quantum physics via non-locality. And then the energy considerations, basically looking at energy from the quantum vacuum, energy from sonoluminescence, and non-viable energy approaches like possibly cold fusion and magnetic motors and things like that. From this point forward, this part of the book covers the computational tools and conventions needed to have a universal language when we talk about these things, what kind of computer programs are applicable for evaluating breakthrough propulsion physics, translating different areas of physics into a common engineering theme, and then how to do pioneering research. Well, the first thing we need to look at is to understand the fact that spaceflight is really hard, folks. If you look at this log scale, you find that as we go further and further out of the solar system and further through the Kuiper Belt, out to the Oort cloud and out beyond all the way to Alpha Centauri, which is about just inside of 1 million astronomical units, about 500,000 astronomical units. You see that the technique and energy demand, infrastructure, and change in velocity gets harder and harder and harder and harder. So keep this picture in mind as we progress further into the talk here. When you look at that picture, you want to say, well, if we're going to have a propulsion technology, how much propellant is going to be needed? We're going to look at an example, propellant required to fly the mass of a space shuttle orbiter past 4.3 light years. So we have a 3-axis chart here showing propellant mass increasing in this direction on that axis, and then rocket efficiency given in terms of its specific impulse in seconds increases from the well-known Orion fission bomb propulsion to the antimatter rocket to 50,000 second specific impulse. So rockets get better that axis. And then, of course, we have mission duration. The trips get longer along that axis. And what we learn from this kind of thing is, when you look at this, you see that with specific impulse in the few thousands of seconds, you're going to need about 10 billion supertankers of propellant in order to get you anywhere. But as the specific impulse increases, then the propellant mass drops dramatically, and that's very nice. However, consequently, the duration of the mission is going to be 1,000 years. If you want to shorten the mission to more reasonable within a lifespan, then as you see, the propellant requirement just skyrockets back up again. And that's what you learn from this using conventional Newtonian physics. And this is what the purpose of our research is about, is how do we overcome this terrible issue? Well, Bob Frisbee, who's now retired from the Jet Propulsion Laboratory, did a study in our book. He gave us a 95-page chapter 2. And here's a graph of the cruise speed velocity of an interstellar mission versus the trip time. And then each of these diagonal bands represent interstellar features or planetary features and interstellar features at increasing distance. For example, the heliopause is at 100 AU along that line, and the gravitational lens of the sun is at 550 AU here, and the Kuiper belt is 40 to 1,000 AU in that band. The Oort cloud lies within this band, and this is interstellar distance from 4.3 light years to 40 light years, so that would be a vision mission. So you're going to look at the fact that the lower the cruise velocity, the longer it's going to take to get there. The faster you go, the less time it's going to take you to get there. And then we compare against that requirement of the propulsion capabilities that are going to be able to meet those requirements. So here Bob Frisbee took a look and saw how these propulsion technologies, NEP is nuclear electric propulsion, and so how they match and how they cut across the slice of the distance versus time versus speed axis, and then here the upper part of the propulsion capabilities that meet the interstellar mission on matter, antimatter, beamed energy, and fusion ramjets. So Bob also took a look at the limits of interstellar flight technology. He looked at those propulsion concepts, and he applied two filters: a delta V capability, in other words, the change of velocity needed to leave the Earth and to get to the cruise speed you need. The infrastructure requirements are like how big can you build your tanks to carry the propellant, as well as radiation shielding from the propulsion system and so forth. And then the technology requirements on building it. And you apply these three filters, and you see for that nice big list of possibilities, they start getting whittled down into very few number of possibilities. Several of them are questionable, and only three of them are definitely yes, they survived all three filtering. So it's not very hopeful. So propulsion technology, this tells us that propulsion technology, even if pushed to the limit of underlying physics, is basically inadequate for timely interstellar flight. To circumvent these limits, we got to have a new propulsion physics of some sort. Even if the desired goals are impossible, investigating physics in terms of spaceflight introduces new perspectives towards solving the lingering mysteries of science. More optimistically, if new propulsion physics is discovered, a new class of technologies would result in revolutionizing spaceflight and enabling humanity to reach to go to the stars. Here's a little graphic that Marc likes to use, show people. It's history repeating itself. To exceed the limits of prior technology, we want to seek entirely different technology. And that was given from a book by Foster titled Innovation, The Attacker's Advantage, published in '86. Here he was showing that the masters that have mastered a certain type of technology are using incremental evolutionary approach to improve the technology until its performance flatlines. But revolutionary pioneers engage in research and develop disruptive innovations that basically lead to revolutionary technologies that go way above the performance flatline. So basically, we're looking at comparing evolutionary research to revolutionary research. We master the known, like how we mastered the sailing technology on the sea and advanced it, vacuum tubes. And then here we have piston-driven propeller fighters that were advanced, and then the lunar landing on the moon with the future return to the moon concept. So this is what an example of evolutionary research mastering what we already know looks like. And then revolutionary research leads to the invention of the steam engine, which went way beyond the concept of using sails to generate thrust. Solid-state transistors, the jet engine, and hopefully in the future warp drives are an example of revolutionary research. The required breakthroughs that we discovered in the Breakthrough Propulsion Physics program at NASA is we've got to look at these three things: mass, speed, and energy, because we need new propulsion methods that eliminate the need for propellant or beaming energy. You just don't want to take so much with you. How can we have a fast interstellar trip without having to drag all that power with you or all that propellant? The energy source is the big driver of the engineering. Speed, discover how to circumvent existing limits like light speed limit to dramatically reduce transit times, and that leads to faster than light considerations. And energy leads us to what methods do we have available to power these types of technologies or these types of physics. The state-of-the-art assessment that we've looked at now shows that no breakthroughs are imminent at this time. Most research that's being done are at steps 1 and 2 in the scientific method, which is just defining the problem and collecting the data theoretically and some empirically. Some research has gone on as far as steps 3 and 4, which is forming hypotheses and testing it. And then the degree of activity is usually dozens of research. They publish directly related papers. They publish directly related to goals. Okay, I guess that should have said their papers were directly related to goals. Hundreds of researchers covered related basic physics, non-rigorous and fringe work, damages credibility, impedes progress. So there's a lot of this going on, and this is the problem that has to be avoided, because this is what hurts us where it concerns federal policymakers when it comes to time to asking for funding for these type of projects. When we look at linking physics to breakthrough spaceflight, we're looking at the rigorous foundations of the known physics that we're looking at now, like quantum vacuum, zero-point energies, dark energy, dark matter, the Big Bang, and quantum entanglement and teleportation. And what we're asking is, what are the unresolved questions in these areas of physics? And then we look at the goal-driven visions, like going faster than light and going to the stars. What are the critical issues and unknowns of the physics in these? And we find that there's a collision where these two sides intersect. Their intersection reveals the important problems that need to be solved for a given breakthrough propulsion concept. And this is the foundation of the book, is looking at rigorous foundations of what we know in physics and what are the unknowns, and then what we desire for our future space transport system for interstellar travel, and then where their intersection occurs is what we are doing in the book to explain. So here are the vision-driven goals: mass, speed, and energy, as I described earlier. And then here's the goal-driven vision concepts and categories. And then here are the rigorous foundations of science that we know. We know what's here, the trades, the theories, and the curiosities that come out of those areas of science. And then in the middle are the important problems, the intersection. And you can see it's quite a detailed chart of very highly interconnected concepts. And it's too long, there's not enough time for me to go through this, but these are all the concepts that we evaluated in the book, in those 22 chapters. But we'll go in and look at a couple of these topics. The book's table of contents is laid out like this. We have the foreword written by Burt Rutan. We originally had Arthur C. Clarke, but he died while he was reading the manuscript, so we asked our good friend Burt Rutan to replace him and do that for us. So we have the contextual history of breakthrough propulsion physics. It was done by Paul Gilster, who's a space journalist. He has the Centauri Dreams website. Here's Bob Frisbee's chapter. Marc Millis has the chapters on space drives. I've got gravity control. George Hathaway in Toronto has gravity and superconductors and non-viable mechanical devices. These are anti-gravity gyros, which have been tested and shown not to be anti-gravity. They basically are non-viable anti-gravity devices. The Yamashita examination was done by Siegenthaler at the Air Force Academy. It's electrogravity unification. That was a null test. Townsend Brown lifters. We had 2 chapters cover that because that was a long, very old, several-decade-old concept that people have been fighting over. We finally found out that Townsend Brown lifters have nothing to do with zero-point energy, nothing to do with electrogravity. It's not even ion wind, it's neutral particle wind. And we had testing done at Sandia National Laboratory by Miller et al. And Canny is a private investigator scientist in the defense industry who did his own set. And then we had all these other topics that we've covered. Thrusting against the quantum vacuum, inertia as a stochastic electrodynamics, relativistic spaceflight, faster than light topics, faster than light communications, space powers, zero-point energy, sonoluminescence, free energy claims, computational tools. So now we're going to get into a couple of the topics, warp drives. All right, so we look at warp drives and we ask the question, is it possible? And the answer is yes. Einstein's theory is where a warp drive came from. That's where Alcubierre discovered a metric by looking at how do I want to move a ship through space at warp speed? How does it work? The ship looks like it's surfing on a wave of space-time faster than light, but yet the reference frame the ship is in, it's not violating the special relativity principle because the spaceship is within an inertial frame that's always traveling less than light, but it's the remote observers outside that warp bubble that's set up by negative vacuum energy that creates this warp drive effect. When they're way outside looking at this, they see this thing transiting space at superluminal speeds, and it's absolute superluminal speeds, not effective. The energy required, however, is extremely high on the order of stellar or planetary negative mass equivalents because you're pulling energy out of the vacuum. It's called subvacuum energy, and this is the most difficult thing to engineer. Traversable wormholes are a different genre. Nothing moves except the traveler. You set up a negative energy shell, and this is a fictitious diagram. This is not what a wormhole looks like. This is called a Flam diagram, and a Flam diagram is a constant picture in time and radius, and we're looking at it in constant angle theta. And so this is like taking a spherical surface, and we're just taking a slice through constant time in one angle. So basically, you're going to have a throat with negative energy that has a repulsive gravitational force. It pushes space out, holds the throat open, keeps it from collapsing. There's no event horizon or singularity like in a black hole. So travelers should be able to go inside that mouth and go through the throat without getting torn apart and come out the other side. You might start at point A, which is the Earth, and you arrive at point B, which is Sirius. This is normal space. This is the normal space-time continuum that you would normally otherwise travel through, but this is a shortcut through hyperspace link, and you get there in just a matter of seconds. There's a wormhole in Times Square, wormhole out in orbit around the sun, and you can see it kind of distorted. There's a galaxy there. Wormholes are anti-gravitational. They're like I can't think of it right now, like a convex lens. Wormholes actually act more like a spherical Christmas ornament, a spherical lens. So the image on the inside coming from the other side of the wormhole mouth is basically distorted and inverted. Here's a flat wormhole. Wormholes can take many shapes. They can be spherical, they can be flat, they can be rectangular, they can be polyhedral, and so forth. So here are the concepts of warp drives and non-locality. Basically, the unresolved issues are the unobtainable amount of vacuum energy, negative 10 to the 40th joules required to create a 100-meter diameter warp bubble so that you can only have a warp of only 3 kilometers per second. It's still bad when you even go down to the speed of a snail's crawl. When you're down as low as a snail's crawl, it's about negative 10 to the 30-something joules. So this is based on the energy study done by Matt Visser and his colleagues who looked at the gravitational interaction between the warp bubble, the spaceship, and the warp effect in the space-time, and the energy conditions. And basically, they discovered that warp drives are just impractical. If you're going to have this much negative energy pulled out of the vacuum, but basically it's impractical to use. You have the native energy conditions, the conditions on what allows you to create that kind of energy out of the vacuum. Controllability, there's a causal disconnect. It seems like when you create a warp bubble, the starship is not able to causally connect to it. You're not able to control it. So that might be a problem. You always have closed time-like curves or time machines in warp drives and wormholes. And momentum conservation hasn't been evaluated. I must caveat that by saying that Einstein's general theory field equations already have conservation laws built into them. It's just that they haven't been demonstrated explicitly by any of the theorists. John Kramer is working on quantum non-locality by looking at retrocausal communication. In other words, communicating backwards in time by way of a quantum entanglement experiment. So this is what the book sections look like for warp drives and wormholes, and interconnecting all of the rigorous known things, the unknown, the interesting curiosities, then the hypotheses and test of the vacuum fluctuations that are needed to create the negative energy, issues and unknowns, and the concepts of the goal vision driven, of the goal driven visions. That's right. Here's John Kramer's experimental design for a retrocausal experiment for FTL signaling. And I don't have too much time to talk about that, but that's in the book. This is Marc Millis' notion of space drives. He's looking at, without violating momentum and energy conservation, is there a way we can manipulate space-time or inertial frames that could create a space drive that looks similar to a differential sail or an induction sail or a diode sail? And these are just for illustrative purposes only. And he's looking at thrust and pressure and area calculations as a way of deriving a conceptualization of these things. And this is, in other words, a bubble of some sort or a change in inertial frames will push on matter in space. And so this is what he's kind of thinking in his mind he would like to see happen. And then here's another one. This is the soap bubble analogy of space-time being warped in such a way that it pushes you forward. Okay, and so this is the inertial frame modifications, propulsion. So these are the concepts being explored, like Bob Ford's gravitational dipole, Martin Tamar's frame dragging device, and here are the concepts that are involved in the rigorous foundations and curiosities, and then the goal-driven visions, concepts and categories, and then everything that intersects in between that needs to be studied. Space drive science issues. There are more than 24 approaches to eliminate specific issues and opportunities. There are objections and objectives, conservation of momentum, net external thrust, energy conservation, because remember, Newton's third law says action equals reaction, and we don't know of anything that has reactionless drives. Warp drive is probably the closest, I think, to meeting this definition, because there is no use of Newton's third law. It doesn't need to apply. Traversable wormholes, that's a different story. A traversable wormhole is a fixated thing in space. It's a fixed tunnel. The explorer is doing the moving. He's going to be in a little rocket. He's going to have to expel propellant in order to move forward through the wormhole. But that's okay, because the wormhole is a shortcut, so it gets him to interstellar distances very quickly. So there's looking at unresolved curiosities like inertial frame fundamentals. We don't know, basically from Einstein's theory, where inertial frames come from. We don't know how they are, what's the fundamental basis of it. General relativity is built out of inertial frames, but we don't know that much about it other than what Mach's principle. Space-time density, this is interesting. This is not an experimental error here. Marc wrote this as 10 to the negative 1 plus or minus 26 kilogram per cubic meter. This is the range. He's saying we're ranging from 10 to the negative 1 to 10 to the 26, and I told him that was a bad way of writing that. Quantum vacuum density, this is, again, a range. It's not representative of a measurement error. This is, I think the better table is right there. This is the better table. I told him we want to explain this. We want to look at the density of space-time, because this gives us an idea of what can we do to manipulate inertial frames or bend space-time. So we look at the density of known matter, baryonic plus dark matter, and it happens to have the same mass density as dark energy, based on the measurement of type 2A supernova redshift far out in the edge of the universe. The mass density is 10 to the negative 26 kilograms per cubic meter. The energy density is a nanojoule per cubic meter. If you take the electromagnetic zero-point energy and you integrate it up to the nucleon Compton frequency, this is the energy density. This is the mass density you get from that energy. I think this would be 10 to the 113 joule per cubic meter. And then look at these numbers and compare them to the Young's modulus calculated from general relativity, the stress versus strain, which is the gravitational coupling constant right there in Einstein's field equations, relating the geometry, warp on the left, and the space and the matter energy on the right. And this is the coupling constant multiplied by that matter energy. And here's the units. And then here's what you get in terms of kilogram per cubic meter. It's on the order of 10 to the 25 kilogram per cubic meter. Shows you that space is extremely stiff. Space is extremely stiff. The vacuum CPE, if you can add it all up, would give you something that is not within that ballpark, but it gets close. And it shows that all matter and energy that we have access to cosmologically is very weak compared to what you would need to bend space. And of course, up to the Planck limit, space is even stiffer. Inertial frame dragging. Are the reference frames against which acceleration is measured. Inertial frames are a property of space-time that is not fully understood, other than we have Mach's principle times 10 versions of Mach's principles out there with their own ideas of how to explain inertia. Space-time is worked by the presence of mass energy via the Einstein equations, which is given here. You see a ball of matter is going to bend space around it, and the rubber sheet is in that nice rubber sheet illustration. Gravity is the force that we associated with the geometrical curving of that space, and that's what we would call an inertial frame gradient. General relativity also predicts minuscule dragging of inertial frames in the vicinity of rotating masses, and this is well predicted by general relativity, and it's called the Lens-Thirring effect, or the gravitational Faraday effect. And unfortunately, the NASA Gravity Probe B was not successful at measuring it because there were problems with the high sensitivity crystal gyros that they used. They were just, there was a problem. There was technical problems. They could not verify the frame dragging effect at all. Martin Tama basically is in Austria at the Austrian Research Centers. It's now the Austrian Institute of Technology. They've changed. He was looking at rotating rings, putting them in a cryogenic dewar, liquid helium, and putting the ring on a holder, a metal holder, and spinning them up a few hundred RPM. And basically, he put accelerometers all around these, and he began seeing an unusual force. He began mapping the force and measuring it, and he discovered what looked like a gravitomagnetic effect, something similar to the Lens-Thirring effect, but with a very high gravitational coupling constant, like about probably 18 orders or maybe 10 or 12 orders of magnitude larger than general relativity would predict. But it was rather high, so he developed a theory thinking that possibly the superconducting states of the metals in this liquid helium were coupling with the gravitational field somehow and creating an anomalous constant value of a frame dragging force on the outside of this instrument. As time went on, he interacted with our group, and we gave him a lot of input, and he took our input to redesign an experiment 2 or 3 times to measure. He graduated away from accelerometers and went to laser gyros. He even obtained the laser gyros that are used on Soviet ballistic missiles, which are highly sensitive. He reproduced the effect, only the coupling constant got smaller, and then he finally got to the point to where he had to take the rings off. He could measure the effect just with the holder. Then he took the holder off, and now he's measuring the same effect with just the helium. So the theory is no longer any good. It's a bust. He's still getting data, still measuring the force, but there's no theory to explain it. I'm going to have to skip this. This is Jordan Clay's chapter in the book, looking at the quantum vacuum, zero-point energies, and the dynamical Casimir effect. You take a Casimir cavity, but you oscillate one boundary in the cavity, and there is a net thrust that's generated in keeping with F equals ma and the third law, and you can push against the vacuum fluctuations. You generate a really, really minute thrust. And it is not quite measurable yet. I think we're just on the verge of possibly designing an experiment to actually measuring this in the near future. Here are the thrust equations. We looked at sonofusion, the Rabanek's husband-wife team at Glenn Research Center in Cleveland looked at the possibility of whether sonofusion could be a power source. It's not an open and shut case yet. Sonofusion does exist and it does produce power, but it's basically a chemical acoustic system, and it is not going to be any breakthrough power at all. It's not going to provide any kind of energy to lead to a breakthrough that we could depend on. Curiosities, as you guys may have heard by now, the Voyagers and Pioneers, as well as other spacecraft that have been reported in the last few years, have been feeling an additional sun-centered attractive force on them. And it goes beyond Newton or Einsteinian gravity. So basically, there's a new force of gravity acting. The systematic analysis of all these forces measured by all the different spacecraft are showing a demonstrable force that's consistent, it's repeatable, it has the same elements. However, we don't know what the source of it is, and so people are looking at alternative theories of gravity. If we look at more curiosities involving dark energy, dark matter, and the Big Bang, there might be things that these things will tell us. These things may tell us something about space-time and vacuum energy that might lead us to exploring some unknowns that could get us to breakthrough propulsion. And here's what the mysteries of physics would look like as we covered them in our book. And they're all interconnected to all these different concepts. And last, Marc's particular challenge was, as a NASA program manager, he was tasked with having to beat down the skeptical academics and allow incredible scientists and visionaries who are credible people, who publish in peer review, who are out-of-the-box thinkers, be able to come forward, get some support to be able to study some of these interesting problems. So we looked at what are the features that we want in being a visionary pioneer. We want to combine vision and credibility to consider the possibilities, research rigorously and impartially, and judge others' rigor and impartiality, but not the feasibility. That's one important characteristic you've got to have. You want to do small increments of progress, affordable, less provocative, so you don't stir controversy. Emphasis on physical observables, and use appropriate comparisons with energy, for example. In spaceflight propulsion, the key driver is rocket efficiency, or propulsion efficiency as measured by the specific impulse. You cannot use specific impulse for warp drives, or wormholes, or quantum vacuum thrust, because it has no meaning in those genres. The specific impulse comes out of the rocket equation, which is Newtonian physics. So you've got to talk in terms of energy. And then seek and apply qualified critiques by bringing in outside peer reviewers who are interested and willing to examine these things, look at the rigor, and judge their effectiveness and whatnot. My concluding remarks are, interstellar flight requires discoveries in physics rather than just technological refinements. Physics has advanced sufficiently to where research towards spaceflight breakthroughs has begun, and it's been in progress since the mid-1990s. Even if desired breakthroughs are impossible, at least the path of this study provides novel approaches to scientific investigations to continue looking into those curiosities of nature and the cosmos, like dark energy, dark matter, and those anomalous forces acting on our spacecraft far outside the solar system. And if the breakthroughs are found, spaceflight and much more will be revolutionized. Thank you very much.
And we do have time for questions. Peter.
Is there any thought to use the known properties of UFOs as a guide to your thinking?
I couldn't hear him. Can you tell me what his question was? Okay. Probably a good idea to use the microphone.
The question was, is there any thought to using the known properties of UFOs as a guide to your thinking and research?
I'm still having trouble hearing. I don't know what's going on up here.
The question is there any...
Are you asking if any of the work we're doing is up? Okay.
Is there any application or wisdom to be taken from UFO research that might help your research?
The answer is yes and no. Secretly yes and overtly no, because the mainstream academics don't like the topic of UFOs, and we really don't have any credibility with them, especially with policymakers and decision makers in charge of funding and programmatics. They don't want to hear the topic of UFOs. So for the purpose of doing this officially, we don't bring in UFOs, but we did consider it under the table. And yes, there is a subset of us who have looked at UFO data, and we've looked at all the physical events and physical descriptions that are provided by investigators from Jacques Vallée to yourself and whatnot, and George Hathaway and so forth. And we've been able to use that data as input to give us an idea, and that data does drive the concepts that we did derive later on that went into the book and went into the original NASA program, like warp drives and wormholes. For example, at the Millis, Utah ranch, that I used to work for Bob Bigelow for 6 years, we had the experience of one scientist and one investigator seeing a wormhole, what looked like a wormhole, open up with a creature crawling through, and then the ranch owners had actually seen an opening in the sky in broad daylight with the triangular craft that came through it. Well, that's an example of data that indicates there's a wormhole involved. I mean, geometry tells you what a wormhole looks like when it intersects our space. It appears as a very bright, intensely bright point of light, and then as the intersection gets larger and larger, then it opens up and you begin to see the hole. And things will be going in and out of it. So that's an example of 2 data sets that we verified at the Millis, Utah ranch that match what I know as a physicist a wormhole would do. Work-wise, we haven't seen UFOs do performances that adhere to the warp drive, because the warp drive basically it's just between stars, and we don't see UFOs warping anywhere, warping around. We see them doing 90-degree turns and rapid motions. They disappear and reappear. That one is undetermined yet. I would think the wormhole is a good possibility still. I'm trying to think of anything else. And I think anti-gravity, we have anti-gravity in Einstein's general theory of relativity, and I cover that in my chapter in the book, one of my 3 chapters. There are other aspects of anti-gravity, the properties of negative vacuum energy that will create a repulsive force that allows something to levitate up, and UFOs do exhibit that. So then Hal Puthoff's polarizable vacuum model. It's a different form of relativity where instead of a space-time, you envision a space-time as a polarizable vacuum of the quantum zero-point fluctuations. And if you exert a field on that medium, the fluctuations are polarized. That creates a space-time bending effect similar to warp drives or wormholes. So we see that. We see a lot of aspects of what he predicts.
Eric, can we take 1 or 2 more quick questions? One here.
Well, I was going to say there's a question way in the back there.
Right, but here first.
Oh, okay.
I hate to continue the verboten topic of UFOs, but I'm driven to ask if you know the name Bob Lazar.
About what?
The name Bob Lazar. You don't know that name? He claims to have worked in Area 51 and to have worked with captured UFOs and to have investigated the physics of propulsion. And he states that, I believe, element 113, which is as yet undiscovered on Earth, is an island of stability in otherwise unstable regions of nuclei, and that in element 113, the strong nuclear force extends slightly beyond the nucleus, and aliens have discovered a way to amplify that force and use it to create artificial wormholes for transport.
Oh, interesting.
So, I know, I'm sorry. This is hard to do shortly, but that is one avenue. I think the wormhole idea is the solution to this problem, and that is one bit of forbidden knowledge that you might use in the future.
Okay, thank you.
Thank you.
But yeah, there's actually 2 questions back there. The gentleman at the end of the table,
Okay,
right behind you.
our questions really have to be brief.
My name is Sky Nelson, and my question is, you mentioned retroactive causation as a means of communicating into the past. Can you elaborate on how that would impact space travel? So how retroactive communication into the past could actually influence space travel? Is there some connection there that you were making?
Which part of that do you want me to elaborate on?
How retroactive communication, where you're just transferring information back and forth, you're just transferring information, does that actually travel?
No, there was a thought that, does it apply to space travel? We don't know. I personally don't think so. FTL communications, it's just going to lead to FTL communications. I don't think that, Marc put that on the slide probably because he wanted to leave that question open to be addressed. And right now, John Kramer's research is specifically for a communication system, and it doesn't have any application for space travel. They're entanglement or teleportation.
Okay, again, thank you very much.